For as long as telescopes have been pointed at Saturn, its rings have looked like the one truly permanent feature of the solar system. A structure so vast, so symmetrical, and so seemingly ancient that nobody seriously questioned whether they'd simply been there since the planet itself was born. Then spacecraft data quietly demolished that assumption. Saturn's rings, it turns out, are almost embarrassingly young. So young that dinosaurs had already been walking the Earth for tens of millions of years before they existed at all. And in February 2026, a team of researchers finally worked out why. A catastrophic collision between two of Saturn's moons, one of them the planet's largest, that reshaped not just the rings, but the tilt of Saturn itself. The story of how we came to understand Saturn's rings stretches back more than 4 centuries, to 1610, when Galileo Galilei became the first person in history to point a telescope at the planet. What he saw baffled him. Saturn appeared flanked by 2 smaller companions, almost like handles on either side. 2 years later, those handles seemed to vanish entirely, only to reappear a couple of years after that. Galileo was witnessing a real phenomenon, not a fluke of a crude instrument. He simply lacked the resolution to understand it. Saturn's axis is tilted by roughly 27 degrees, meaning as it orbits the Sun, its rings alternately present themselves edge-on to Earth, effectively disappearing from view, and then open back up into their familiar, sweeping shape. It took nearly 50 more years of improving telescope technology before Christian Huygens correctly identified Galileo's mysterious handles as a genuine ring encircling the planet in 1659, the same year Huygens also discovered Saturn's largest moon, Titan. From there, discoveries accelerated. In 1675, astronomer Giovanni Domenico Cassini spotted a distinct gap within the rings, a division that today bears his name, while also identifying 4 additional major moons: Iapetus, Rhea, Tethys, and Dione. By the 19th century, astronomer James Keeler had demonstrated something crucial. The rings weren't solid sheets at all, but countless individual particles, each independently orbiting Saturn according to its own trajectory. Still, the true scale and complexity of the system remained essentially invisible until spacecraft finally arrived. Pioneer 11 and the twin Voyager probes, passing through in the late 1970s and early 1980s, revealed that what looked like a handful of broad rings were actually made up of millions of individual, tightly packed ringlets. The real transformation in our understanding came with NASA's Cassini spacecraft, which spent more than 13 years in orbit around Saturn, threading itself through gaps in the rings, skimming close to their edges, and finally, in its last act, diving repeatedly between the planet's cloud tops and its innermost ring before deliberately plunging into Saturn's atmosphere to end the mission. The data it returned rewrote nearly everything scientists thought they understood. Saturn's rings, Cassini confirmed, are almost impossibly thin, in most places somewhere between about 30 feet and just over half a mile thick, and yet they stretch outward from the planet for more than 170,000 miles. Named alphabetically in the order they were discovered rather than their actual position, the main system includes the D, C, B, A, F, G, and E rings, along with an extremely faint, far more distant Phoebe ring out near the orbit of the small moon it's named after. Small shepherd moons, including Pan, Daphnis, and Prometheus, orbit directly within or alongside the ring system, their gravity actively confining ring particles into narrow, well-defined bands rather than letting them spread out into a diffuse haze. Cassini also determined the rings are composed of roughly 99.8% water ice, and particles ranging from grains barely larger than sand up to chunks the size of a small mountain. The ice's high reflectivity explaining why the rings appear so brilliant even through Galileo's primitive 17th century telescope. But it was combining 2 of Cassini's measurements, the rings' composition and their total mass, that produced a genuine scientific bombshell. Over time, the constant rain of micrometeorite impacts and interplanetary dust should steadily darken clean water ice, contaminating it with darker material and dulling its brightness. Cassini calculated the total mass of the rings at approximately 16 quadrillion tons, an enormous number, but still less than 0.02% of the mass of Earth's own moon. Working backward from that mass and how much darkening dust it could plausibly have absorbed, researchers realized the rings simply hadn't been exposed to space long enough to look as bright and clean as they do, if they'd truly existed since Saturn's formation 4.5 billion years ago. Instead, the evidence pointed to an age of somewhere between 10 and 100 million years, a blink of an eye in solar system terms, meaning Saturn's rings likely formed roughly 150 million years after dinosaurs had already been walking the Earth. That left an obvious question hanging over the entire system. If the rings are that young, what actually created them? The physics behind ring formation in general had already been worked out back in 1849 by astronomer Edouard Roche, who calculated that any moon straying within a certain critical distance of its host planet, now called the Roche Limit, would be torn apart by tidal forces stronger than the gravity holding the moon itself together, its shattered remains spreading out along its original orbit into a ring. For Saturn, That critical distance works out to roughly 54,000 miles, closely matching the location of the outer F ring. But knowing the mechanism that creates rings in principle didn't explain what specific object had actually met that fate so recently in Saturn's long history. In 2022, researchers at MIT proposed an answer. A hypothetical, now-vanished moon they named Chrysalis, orbiting somewhere between Iapetus and Titan, whose orbit was gradually destabilized by Titan's gravity until it was pulled too close to Saturn and torn apart, its debris eventually settling into the rings we see today. It was an elegant hypothesis, but when researchers at the SETI Institute, led by astrophysicist Mariame Chuk, ran detailed simulations of that scenario, publishing their results in February 2026, the numbers told a different story. Rather than being pushed inward towards Saturn and destroyed by tidal forces there, their models showed Chrysalis would far more likely have simply collided directly with Titan itself, with most of the resulting debris either being absorbed by Titan's own gravity or flung entirely out of the system, never actually forming rings at all. The team noticed something else troubling in their simulations of the Chrysalis scenario. A small, oddly shaped, chaotically tumbling moon called Hyperion kept getting ejected from the system entirely during the chaos. But Hyperion is very much still there today, tumbling unpredictably just as it always has, and its orbit is locked in a tight gravitational relationship with Titan. That single inconsistency became the key that unlocked the entire mystery. Chuk realized Hyperion wasn't simply a survivor of some earlier upheaval, it was likely a direct product of it. Reworking the model from the ground up, treating Saturn's rings, its many moons, and even its own axial tilt as pieces of one single interconnected system rather than separate, unrelated puzzles, the team ran dozens of detailed simulations spanning hundreds of millions of years. Their results pointed towards something considerably more violent than a moon quietly torn apart by tides. A direct, head-on collision between Titan and a second, previously unknown moon roughly 4 times more massive than the earlier Chrysalis hypothesis had proposed, an object the team named Proto-Hyperion, since present-day Hyperion appears to be the leftover wreckage of that impact. In their simulations, this collision between Proto-Hyperion and an earlier, smaller, more circular orbiting version of Titan, which the team called Proto-Titan, occurred in 42 out of 60 separate simulation runs. In the handful of runs where no collision took place, either Proto-Hyperion or Iapetus was instead flung entirely out of the Saturnian system. The chain of events, as the team reconstructed it, began roughly 400 million years ago, when Saturn briefly slipped out of a stable resonance relationship with the solar system's other giant planets. Orbital resonance occurs when two bodies' orbital periods lock into a simple, repeating ratio, and the small gravitational tugs from each repeated encounter gradually accumulate into a far larger effect than any single pass could produce alone. In Saturn's case, this shift destabilized Proto-Hyperion's orbit, locking it into an extremely strong 2-to-1 resonance with Proto-Titan. For every single orbit Proto-Titan completed around Saturn, Proto-Hyperion completed 2. That resonance dragged Proto-Hyperion rapidly inward, setting it on a direct collision course with Proto-Titan, while its gravity simultaneously yanked Iapetus into a steep, unusually tilted orbit along the way. Eventually, the two moons' paths crossed entirely. The aftermath reshaped Titan permanently. Today's Titan, larger than the planet Mercury and Saturn's largest moon by far, is famous for its thick, hazy, nitrogen-rich atmosphere and its startlingly young-looking surface, marked by surprisingly few impact craters for a body that ancient, along with rivers and lakes of liquid methane. In Chuk's model, the impact with Proto-Hyperion resurfaced huge portions of Titan, effectively erasing much of its older, heavily cratered terrain, while a large share of Proto-Hyperion's mass merged directly into Titan itself. What remained, loosely bound debris that never fully merged, gradually reaccreted into the small, misshapen, unpredictably tumbling moon we now call Hyperion, whose current age, estimated at 400 to 500 million years, its unusually low density, and its genuinely chaotic rotation all line up remarkably well with what a body formed from loose collision debris should look like. Not long after forming, Hyperion was captured into its present tightly locked resonance with Titan. Titan itself didn't emerge unscathed. The force of the impact pushed it into a far more elongated elliptical orbit than it had before, a shift that had actually begun even earlier, as soon as its orbit became resonant with Proto-Hyperion, then accelerated sharply after the actual collision. And in a genuinely strange twist, Cassini data shows Titan continuing to migrate outward from Saturn at a rate of roughly 4 inches per year, considerably faster than existing models predicted, a rate that lines up neatly with the kind of momentum such a violent collision would have imparted. Titan's growing, expanding orbit didn't just reshape the moon itself. As its path swept outward through the Saturnian system, it began exerting gravitational influence on Saturn as a whole, altering the planet's own precession. the slow wobble every spinning, slightly non-spherical planet exhibits, similar to a slowing top beginning to tilt as it spins. That shifting precession eventually locked Saturn's axis into resonance with Neptune's orbit, and the only way that particular lock could be sustained as Titan kept drifting farther away was for Saturn's entire rotational axis to tip over into the dramatic 27-degree tilt we observe today. Since giant planets are generally expected to form with close to zero axial tilt, Saturn's pronounced lean had puzzled scientists for years, and this newly modeled collision provides one of the most compelling explanations for it yet proposed. For roughly the next 200 million years, the reshaped Saturnian system appears to have settled into relative stability, but Titan's slow, continuous outward drift eventually caused one more round of destruction. About 100 million years ago, its shifting orbit locked into a new 4-to-1 resonance with a pair of smaller inner moons, tilting their orbits and eventually driving those two moons directly into each other. The resulting collision, amplified by Saturn's own powerful tidal forces, shattered both moons into an enormous cloud of debris. Some of that wreckage eventually reaccreted into small new moons. Some was lost to space entirely, and the remainder spread out into the thin, brilliant disc-shaped structure we now recognize as Saturn's rings. Every strange, previously unexplained feature of the Saturnian system, Iapetus's oddly tilted orbit, Hyperion's unusual age and chaotic shape, Titan's thick atmosphere and youthful, lightly cratered surface, its unexpectedly rapid outward drift, Saturn's own 27-degree axial tilt, and finally the rings themselves all trace back, in this model, to a single violent chain of events set off by one collision 400 million years ago involving Titan. Confirming this model directly will likely fall to NASA's upcoming Dragonfly mission, a nuclear-powered, car-sized rotorcraft scheduled to launch in 2028 and reach Titan by late 2034, designed to fly between multiple locations on the moon's surface, sampling and analyzing its atmospheric and surface chemistry in unprecedented detail, potentially turning up direct physical evidence of the ancient resurfacing this model predicts. The researchers behind the February 2026 study were careful to note that even if every specific detail of their reconstructed timeline doesn't hold up perfectly under future scrutiny, the broader framework, an interconnected system where resonance, tidal forces, and a single ancient collision ripple outward to explain multiple, previously separate mysteries at once, offers a genuinely new way of thinking about how Saturn's complex family of rings and moons actually evolved. None of the individual physics involved here, orbital resonance, tidal disruption, planetary precession, is new or exotic. Scientists have understood each of these mechanisms individually for a very long time. What's genuinely new is recognizing just how tightly interconnected they turned out to be, one ancient collision setting off a chain reaction that, hundreds of millions of years later, would leave behind rings bright enough to make Saturn instantly recognizable through even the crudest telescope. And those rings, spectacular as they are, won't last. Cassini's final orbits revealed that ring material is constantly raining down into Saturn's atmosphere, an ongoing loss of roughly 10 tons of ice every second. At that rate, scientists estimate the rings may only survive for another few hundred million years before they disappear entirely. Saturn's system, it turns out, isn't the timeless, unchanging structure it appears to be through any telescope, ours or Galileo's. It's a genuinely dynamic, still evolving story, one where we happen to have arrived at almost exactly the right moment in its long history to see the rings at all,